Okay, so let's come back at this point to talk about how the electric potential changes as you move around in a constant electric field. So let's start, again, because we know we're sort of building the electric potential out of how it relates to the electric potential energy. Let's start by thinking about how the potential energy changes as you move a test charge around in your electric field. So here E is the strength of my electric field. Q here is the test charge that I choose to move around, and then this D parallel is the parallel distance that I move to the electric field. So again, the potential energy doesn't care about how much you move perpendicular to the electric field, it only cares about how much you move parallel to it. Well, again, this is that's how the change in potential energy can be calculated. How do I calculate the change in potential when I move around in my constant electric field? And so I'm going to take my change in potential energy expression and divide out that test charge. So here we just labeled it Q, here we're labeling it QT, but it's the same thing. It's just whatever charge you choose to put around in this field. And so when I divide out the impact of that test charge, I'm left with the change in electric potential is equal to plus or minus ED. So we'll come back to the plus or minus in a second, but again, notice that this really just cares about what's the electric field, right? What's its strength, how are you moving in the electric field. So the plus or minus cares about which direction you're moving relative to the direction of the electric field. And the D is, well, what distance, how far are you moving? So in this case, if you move with the electric field, you actually want the minus sign. So when you move in the direction that the electric field points, you actually are decreasing the electric potential. When you move opposite the direction of the electric field, you're increasing the potential. So one of the things that this sort of tells us right away is that electric field lines run from high potential to low potential. So because in this picture, our electric field lines run from the positive plate on the left to the negative plate on the right, that means that the left-hand side of this field is actually at a much higher potential than the right-hand side. So as you move to the right, the potential decreases as you move across this field. So what would happen if we took our test charge and released it here at point P? Well, again, that's going to depend. Which way it moves would depend on the test charge, but we know that a test charge will always move to decrease its potential energy. So if I put a, say, positive test charge here, I know that it would move to the right to decrease its potential energy when I released it. If I released a negative test charge from point P, it would move to the left to decrease its potential energy as I released it. So I know that no matter what I do, no matter what kind of point charge I put at point P, as soon as I let them go, they're always going to move to decrease their potential energy. So when I rewrite my equation, sort of my definition for the change in potential, and bring the Q back over onto this side, well, the change in potential energy whenever you release a charge within an electric field is always going to be negative. So that tells me, or at least gives me an indication of what's going to go on with the potential, because making the right-hand side of this equation is going to depend on, well, what's the sign of the charge. So if I have a positive charge, so this is positive, so for the right-hand side of the equation here to be negative, that tells me that the electric potential will decrease. So my positive charge will move from a region of high potential to low potential. So positive charges decrease their potential energy by running downhill. And again, we said this was the left side here was the high potential end, the right side was the low potential end, and sure enough, we know that that's the way that a positive charge will move. It will move from higher potential to lower potential. If that's a negative charge, well, now my Q is negative, which means to keep the right-hand side of my equation negative, delta V should be positive. So what that tells me is that a negative charge, when released in my field, will actually move to increase the potential. So it'll move from a low potential point to a higher potential point. So negative charges decrease their potential energy by running uphill, in terms of the way that we sort of think about how the potential, right, acts like a hill. So my negative charge will move, when you release it, it will move against the electric field. My positive charge, when you release it, it will move with the electric field. Again, if we want to talk about the potential, in the same way that we said if we want to talk about the potential energy, what that really means is that means the potential energy relative to where the potential energy equals zero. So just when we're saying the potential energy, that's really always relative to our choice of a 0 point. And so in a constant electric field, we get to pick where we want the electric potential energy to be 0. And so then we can think of our equation then as the potential energy is now defined relative to this 0 point, depending on whether you're above or below. And sort of the above or below is really just an indication of, well, if you release the charge, it's going to go towards lower potential energy, towards a spot of lower potential energy. So that indicates to you where the lowest potential energy spot is for that particular charge. Because again, the potential energy cares about what charge you're releasing in the electric field. So the easiest way to sort of deal with the potential energy is to say, well, if I let my charge go, which way would it go? Let's say it goes in this direction. So as far as it can go in this direction, that's what I'm going to call my 0 point. Now everything else becomes positive because it's going back in the other direction. We've got to play the same game if we want to talk about the electric potential. So what we'll do is we'll say, well, the electric potential means the electric potential relative to where the potential equals 0, and we'll set the potential to equal 0. Oftentimes that'll be where the potential energy equals 0, but it doesn't have to be. And so in fact what we'll end up doing is, so we will tend to say, well, I know that the potential is going to be at its lowest point as I hit the negative plate. So again, this doesn't depend on the test charge. So if I define the potential to be 0 at the negative plate, then again everything else has got to be positively valued. I don't have to make that choice, but again it's sort of an easy choice to make so that I ensure that the rest of my potential values are all positive and I don't end up with some additional sign error.